Good afternoon, everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Engineering program here at Lehigh, and I welcome you to the very first uh, talk for the fall session of the ESE seminars. We've been doing this for about 3 or 4 years now. It was 6 or 8 semesters, and this has been a we've been very successful in bringing out speakers, from various parts of the globe, as well as on various topics that are very pertinent to what the energy landscape is going through. In fact, the title of my talk is The Changing Energy Landscape that has changed within the last 18 months in a dramatic way. And before that, of course, there were changes there too. But I want to kind of show you how much there are. The changes are somewhat cosmetic in the sense that what we set out to do, which is basically to limit uh, greenhouse gas emissions, has to proceed by taking all the actions that are being uh, prescribed by what has happened in the past and as well as what will be happening in the future as we go forward. Just a little bit about my background. I had 40 plus years experience in the business side of energy, starting off with in the fossil generation side, and then the nuclear, as well as later on I had a lot of dealings with the grid itself. Uh, so I kind of proudly like to say I'm a jack of all trades, but I truly am a master of none. I'm always learning as I go forward. So I've been in the academic world for the last almost 10 years now. And so it's really it's very, I find it very um, challenging to look at, what's happening in the field, and being able to kind of translate to, how do we prepare, for the changes that are going to take place. And nevertheless, I am also very excited because there's obviously the answers would come from young minds like yours, and so I'm very optimistic as to what the attributes are going to be. Okay, so there, as a short introduction, we do have a new set of cohorts who have joined, and I welcome them, and they will be with us for at least the full-time students will be here for about 10 months, and the part-time students a little longer. And we also have an audience from industry, from the nearby areas, as well as persons on our advisory council. As far as I can remember from how many have signed up, it was close to 70 or 75. I expect that we will probably top out between 50 to 60 attendees. So I welcome you and thank you for your attendance. Let me see if I can move this slide. Okay, there we go. So a kind of short description of the overview of my talk. These are the 5 bullets. Electricity is going to become a critical infrastructure, if not already there. What will be transpiring the few years in the years forward is how electricity is going to be important, have an important role to play in other industries that is not involved in. For example, manufacturing and process industries. It is probably going to play a large role, mainly because it is going to be uh, uh, perhaps less expensive, and more critically, that it'll be very low carbon or zero carbon. And I don't have to tell you why we need to go zero carbon, because we do have the threat of climate change, and we're seeing effects of that even as we continue our activities. I'm going to talk about the energy transition, there was a lot of activity for the last 5 to 10 years, past 10 years, and we are kind of coming to a new uh, uh, situation. And so I posed a rhetorical question: is there going to be a continued efforts in the energy transition, or is there going to be a reversal? And I want to tell you very plainly and very strongly, I don't think that's the case. I think we'll be tackling the same problems that we attempted to tackle, a few years ago. And the idea of this talk is to kind of show you why I think I feel that way. The third bullet, it shows something that's going to play an extraordinary role in the demand for electricity is AI-driven data centers. It's a phenomenon that has arisen in the last few years, where these very powerful chips can do calculations that are immensely complex and immensely fast, and so much so that the demand for electricity is going to be abnormally high. So you think of a very large load on the grid, as it were, and of course this AI-driven data centers is driven by people who are very, very strong in this market. One of the richest companies, Magnificent Seven, has been used, and they are basically in a position where they would be able to kind of have the demand could be as high as a particular power plant. Um, and so you can see that just the dynamics of that kind of impact will have a change in not only how we do business, but also in the technologies that would be coming forward in the next few years. A very exciting time, but at the same time, we need to also be looking at, how do we address this in the next few decades. Finally, I'll talk about, what the some of the students will be involved in. Obviously, some of the work would be very much aligned, with some of the happenings that are there in the industry. And we have capstone projects that we've initiated for this year. And so I'll give you an overview of that. And finally, give you a kind of an overview as to what you'll hear in the remaining seminars this fall semester. And as far as the questions are concerned, I would prefer that you kind of ask the questions after I finish my talk. But if there's something very pressing and you'd like to ask this question, please go ahead. I don't want to kind of discourage you from asking those questions. Before I leave the slide, I will just mention that we had kind of published some parts of this in the Energy Central journals a couple of years ago. And so if you were to look at this article on power generation trends in 3D in Energy Central, the 3Ds, by the way, stands for digitization and distribution and decarbonization. So those are the 3Ds. Why is electricity so important? And this graph shows really clearly that at least as the graph shows, the GDP per capita, as a gross domestic product per capita, was very highly correlated with the amount of electricity consumption for the Western world, as shown here in this picture graph. The top graph shows the U.S. GDP per capita from years 1929 to almost the present, 2016. And so over these years, electricity played a bigger and bigger role. We cannot transformed ourselves, from the industrial revolution, to the modern age where electricity plays a large role. And obviously it also plays a large role in the prosperity of the nation. The upper two graphs show what is the case for the U.S. and the Western world, Western Europe. And sure enough, if you look at the trend about 50, 60 years later, you see the same trend where electricity generation is more and more embraced by other countries who are trying to catch up, more specifically China and India. And China, you can see when Europe was still struggling. I'm sorry, China was still struggling with uh, introducing electricity, where Western and Europe and U.S. were well along. But you can see they've caught up very fast. And in fact, today they're probably the biggest. They have the biggest grid, and many other attributes are there with China, the largest renewable resources, and they made this change over the last, well, 3, 4 decades. India is, of course, slightly behind, but not too far. It too is kind of prospered from the 1980s, just as China has kind of taken off from there. But you can see that electricity is directly correlated with prosperity. The more electricity there is, the more prosperous the people are. And this is kind of well summarized by this graph. Again, the vertical axis shows electricity consumption per capita now for many countries around the world, not just through the four that I showed before, uh, but plotted against the GDP per capita. So GDP now is on the horizontal axis, and electricity consumption is on the vertical axis. And the size of the bubble is the size of the population. So you can see as you kind of go towards the right hand, uh, the right hand the maximum in the right hand quadrant, you can see some of the most prosperous nation and the most highly consuming electricity consumers are on the right top corner. And the ones that are in brown are the ones which are developing and developed world. They're coming along. And more significantly, you see China is very much kind of moving towards the developed, completely developed nations, and especially with its large population. It kind of shows a very kind of resounding impact. Um, this phrase that no such thing as a low energy rich country is probably a truism, but it's not. Things are always not that straightforward. So we can't just rush all the other countries to be doing what we're doing to be able to be prosperous, and that's because of climate change. Uh, the In the early 2000, this particular millennium, and probably the late part of the 1980s and 1990s, there was a kind of a realization that we are kind of paying a price. That price is because we're using fossil fuels to generate our electricity, or they're mainly the main contenders. We are also kind of disturbing our planet by having greenhouse gas emissions. And greenhouse gas emissions, usually carbon dioxide, have a very large shelf life. So we're kind of adding on to the emissions in fact, uh, from when the Industrial Revolution started. And we're seeing some of the effects. We saw them slightly in the early 2000s, but they're much more prevalent today. And the most deleterious way is in the extreme weather that we are encountering, and generally hotter temperatures, throughout the globe. The average temperature around the globe has been steadily moving up, ever since the late 90s to where we are today. Um, of course, there are probably different camps as to how critical this crisis is, and what kind of actions we need to take. But one thing that became clear and is that we needed to be able to reduce temperature changes to within certain limits by a certain year. 2050 was chosen as a kind of a benchmark, where if we were to be able to reduce or keep temperatures no higher than 1.5 degrees centigrade uh, difference from what it was at the beginning of the industrial age, that there's some control. Of course, we are kind of quite far away from that goal, and in fact, some of the pessimistic uh, issues are that we probably, if we do reach that goal, it's not going to be anywhere near 1.1.5 to 2 degrees centigrade. More likely, it's going to be something higher. So the contributors to greenhouse gas emission is not just a generation of electric power, as shown here, but also transportation and industry, process industries, and manufacturing industries. Transportation, now what I mean by that, of course, is cars that you and I use, as well as freight that's used for transporting commerce. So, all of this transportation were to adopt something that is low carbon or zero carbon, it could be a big contributor to reduce greenhouse gas emissions. Similarly, if the industries, more specifically, the cement industry and the concrete industry, if they were to kind of reduce their carbon or reduce their carbon in their process, that could also be a positive step towards reducing greenhouse gas emissions. Of course, commercially and residential uh, uh, structures also have a contribution. But you can see the big three are right there: transportation, the generation of electric power, and industry. So the hypothesis is if all three of these big pie slices, this one, and this one, were carbon free or carbon low carbon, that we will have done a pretty good job of reducing our greenhouse gas emissions. Again, easier said than done, but that's the challenge that was recognized in the late 1990s to where we are today. So we always have to have a all of the above strategy in generating electricity. Um, and this kind of matrix kind of shows this in a very in a very hopefully a friendly manner. We cannot do without all of them, or or another way of stating that is we cannot just choose one of them to have all of the above, which is reliable electricity, cheap electricity, and clean electricity. And I've introduced a fourth term, again, is very casual and also sexy. Sexy in the sense that we're not doing what we were doing before. And so, solar and wind were in that kind of category. And because they were ways by which we could generate electricity by using the natural resources, that is wind energy, by harnessing wind energy and harnessing solar. And solar, of course, would play a much bigger role. It will continue to play a much bigger role, because that is the source of all nature's energy. Um, we are, of course, using sensors that are able to convert uh, solar radiation and the solar and the light energy through photovoltaic cells. The advantage, of course, is that well, this fuel is free, whereas the other fuels that we use for generating electricity are not free, and so they're not only not free, but they probably have a reserve that is maybe could last, maybe a couple of hundred years, but obviously not for many generations. So this particular matrix with the check marks and the size of the check marks kind of shows how well they fit those specific categories. So if I want to walk you through, is coal as a fuel to generate electricity reliable, or the word that is really very current these days is firm. Reliable means can it be is it available when I need it, and when I need it for a long time or whether a short time, it's always there. So coal can be considered firm, and as can nuclear. Now, coal, of course, adds greenhouse gas emissions, and nuclear is greenhouse gas emissions free. But of course, certain amount of um, greenhouse gas emissions can be attributed to nuclear, maybe in the mining process. But more importantly, the way we generate nuclear energy is by nuclear fission, and that leaves a lot of waste products. And so there obviously they could have an enormous impact if they were not managed properly. And so there is a risk, a pretty strong risk in using nuclear. But we can rely on our experience. We've had about 70 years of practical experience generating nuclear energy. And even though we have had accidents in the US, the most significant one was one that happened at 3 Mile Island in 1979. In retrospect, it was quite well managed. Since then, of course, we've had two events that were pretty major, pretty significant. One was the Chernobyl accident in 1986, and the other was the Fukushima earthquake. And I'll talk a little bit about those two events. The Chernobyl event, of course, was man-made. They were taking risky experiments, while the plant was in operation, and unfortunately, it was not well managed, which led to a pretty severe impact on the site because of the radiation that was leaked, by the Chernobyl plant. It is still shut down. It has been about 40 years since Chernobyl. There were things that happened there that we probably didn't expect, but nevertheless, they kind of showed how nuclear plants, when not properly managed, could be could, could pose a high risk. And but what I'm trying to make, the point I'm trying to make, is here in the U.S. and most of Western Europe and most other countries, the experience we've had with the operation of a nuclear plant has made us that much smarter in reducing the risks. So if you look at what happened at 3 Mile Island, it was quite trivial compared to what has happened since. Now, the Fukushima incident was it was a uh, God, uh, God given, as they say, or something that we didn't have any control over. The Fukushima plant was constructed and designed and constructed for, once to kind of take the design basis was for being able to handle all, but one in a 500-year, one in a 1,000-year event. That kind of design it makes it very conservative in being able to uh, being very conservative in how they put the plant together to make sure that they have a high safety margin. Unfortunately, in 2011, there was a massive earthquake just offshore Fukushima, and so the design basis was it exceeded the tsunami that accompanied this earthquake, and was well above design basis, and really kind of there was a real imminent threat of a loss of coolant accident, or LOCA as it's called. And so we were very lucky in that case. But more so, I think it was the regulations that a country like Japan was able to follow, that you spared something that could have been more disastrous. So it's a long story. I don't want to be long-winded about this. Nuclear fission is still the way that we can still kind of make sure the greenhouse gas emissions are as low as possible. And we're relying on the expertise we have gathered for the last 60, 70 years of, uh, of using of, of using nuclear power plants. Solar and wind, they're not reliable or firm because they're intermittent. Uh, Solar could be less intermittent with storage, but I'll get to that later on. And wind is also, again, with storage. It could be it could be if it could be harnessed. These intermittent sources of energy, it can be smoothed over by using large duration storage technologies that are still kind of evolving today. Um, the one that is most popular is pumped hydro. Think of a hydro plant which could store energy and generate energy at the same time. Uh, that's a pretty clean way of doing business, but there are other issues regarding solar hydro plants that make them less likely to be strong candidates for long duration energy storage. So right now, we cannot brand solar and wind as being reliable, but of course they have other nice features. It has become very cheap. It's dropped in the last 20, 30 years quite enormously, and for sure it's clean. And it fell into this kind of amorphous category called sexy, something new. And so it has it's kind of it got preference as far as looking at what are some of the new resources that could be introduced. Natural gas, a very recent phenomenon, relatively speaking, is because of the fracking technology that kind of allowed us to look at natural gas really in our backyard. Uh, we went literally a couple of decades from a net importer of liquid natural gas to now to net exporter. So this is a remarkable change, and surely some of the technologies that are used in the oil field business has helped. So you need to have this for a balanced portfolio for generating electricity. And nuclear, once upon a time, was considered uh, risky. I joined the energy workforce in the early 70s, and nuclear power plants were many of them were shut down because of cracking in their primary systems. What I mean by that is some of the cracks were discovered, in the primary piping system, and you can see that could be a big compromise on generating electricity. Um, and the technology to be able to detect those was using ultrasonic techniques, ultrasonic pulse echo, as they call them then. Now we have very sophisticated ways of scanning these components. Much like you and I, go can get scanned in a hospital through MRI to look at your body health, looking at anomalies. You can do the same thing for nuclear power plants. So they come back into vogue, and more so because now they are kind of very strong candidates to provide what's called uh, base energy. This base energy is very uh, scalable. It can be handled for long for a large population as well as for long durations. So if I were to look at what has become less sexy is coal and natural gas. And again, I'm using this in a very casual way. It's you can interpret this as uh, something that is more accepted in the present climate, as it were, present environment, present era. So uh, at the same time, coal with carbon capture, which is also been experimented, it has not kind of fallen in the role where it could be cheap. So we need to have these aspects for generating electricity: reliable, cheap, and clean, and you know that. You can see that not one fuel fits the bill completely, but many of them together do a pretty good job. So what has happened in the? Let me just hang on a second. So these are important timelines. Uh, as I said, but from 1970 onwards, the world was a little more, at least, aware of climate changes that are being caused by human activities. Um, there was James Hansen James Hansen is a figure who talked about this, published a lot, and we had our president in the White House installing solar panels. President Carter making sure that it was being recognized. He was probably one of the pioneers, and nobody understood why the White House had solar panels, but he was pretty firm. In the Kyoto Protocol was adopted in the 1990s. As the word Kyoto suggested, was done in the city of Kyoto, Japan, and that basically banded the nations to kind of reduce their greenhouse gas emissions. It was a very informal agreement, which was formalized in the later the Paris Accord in 20. I think I have this date wrong. I think it's 2005, not 2015. I may be wrong. But the other thing that was very fortuitous is solar panel costs dropped 2 orders of magnitude. And these things prices drop because of market availability, and where we're paying like $100 per watt generated, $100 per watt generated in the late 90s, dropped to something like today is like $2 to $4 at most. So that's a dramatic drop in the cost. And the Paris Intergovernmental Panel on Climate Change, came up with a kind of a non enforceable capabilities to reduce. Each nation had a target to reduce their greenhouse gas emissions, to meet certain goals, by 2050. And then, of course, with the new administration that was sworn in after the 2020s, there was this enormous amount of funds that was spent on the Inflation Reduction Act, and the bipartisan infrastructure law. This is again to to demonstrate uh, to demonstrate different technologies that would uh, promote uh, clean energy. And solar and wind generators were widely deployed. It's not just here in the U.S., but also worldwide. So this IRA and the VIL were very effective in being able to demonstrate these technologies because the government was able to back that. So let me see if I got my. Okay. So you can say that the focus was on climate. It was somewhat laudable, but really it was not. The thing that it overlooked, in my view, is that reliability was as important in this prosperity that we encountered using fossil fuels, and there was less focus on the importance of reliability, at least in the way this was being tackled. The present uh, focus is now more on abundance. Abundance meaning being having access to a lot of energy at any time. And again, some of uh, some of the things that did happen was we misinterpreted what adding capacity did to how we actually were able to reach the goals to reduce carbon. I'll come to that in a second. So the abundance required some things that seemed very counter into uh, counterintuitive. That is that we kind of get back to recommissioning more coal plants. Uh, Promote and deploy nuclear power was a wise thing, I believe. But also looking at deep geothermal. I mean, these are genuinely very strongly aligned with some of the things that were done with the Infrastructure Reduction Act, as well as the bipartisan infrastructure law. Fewer regulations are going to be uh, for the future. How long this lasts, we don't know. Some of these reversals of environmental laws, could be not so climate friendly, but definitely speeding up interconnection permits and speeding up NRC reviews of new nuclear builds is very admirable, and I think that it's also well aligned towards meeting some of our goals. So we could say that this present is looking at making sure the reliability focus is not lost. So the word firm is often used to describe this. Now, in its simple terms, a farm resource is something that could be dispatchable. Things that are dispatchable are available anytime, any place. And uh, so firmness is a very, very important aspect of a grid, as is greenhouse gas reduced lower or zero carbon generation. These are two vitally important uh, aspects of the grid. We can say that maybe the focus was solely on the climate change aspects of it in the past, and here we are probably wanting to bring back the firmness aspects to make sure that we always have energy when we want it and where we want it. So if you look at the top three generators of electricity, as I said before, China and India were playing catch up to the Western world. But you can see that today China generates more than 2 times the energy that the next uh, country, USA. And India is half of what the USA generates. Now, focus on the I'm talking about terawatt hours. Our terawatt hours is a measure of energy, and keep that in the back of your mind because it can kind of give you some perspective as to why we did not look at firmness as much as we should have, and why we were somewhat amiss in not recognizing the role of firmness. I mentioned this thing about a diverse mix of fuels. So you look at the capacity of resources in the U.S., and I think this was maybe in the early 20, the early part of this decade. So you have like 30% of your capacity was in coal, 40% in natural gas, 10% in nuclear, and renewables were kind of a tiny lot. Um, Now, if I were to look at uh, what was the amount of capacity and how it's related to the energy we actually use, and this kind of shows what firmness can means. Even though coal was the capacity was 31% part of our total capacity, it was a 48 or 50, almost half the energy content. Again, that's really important. I'll go over that. The capacity of coal in this particular year was 30%, whereas the use of this facility accounted for almost 50% of the energy consumed. And nuclear too has got that same kind of uh, profile. Even though it was only 10% of our fleet, it accounts for almost 20% of our energy use. So this is kind of points out, but capacity is not really important. A megawatt generated is not a megawatt generated is not a megawatt generated. That could be said very clearly. It depends upon where the megawatt is generated because it is used in different ways. And in this particular case, this particular year, we were still, we were thinking that we are increasing renewables, but really we're still relying on fossil fuel to be the provider of energy. In this particular year, in the U.S., we are still uh, looking at about 90% of our energy is coming from I'm sorry, from large resources, and about 70% from fossil-based fuels. So if there was something that was to be learned, nuclear was something that was very desirable, and we needed to continue utilizing nuclear energy because not only is it clean, it may not be sustainable but we do have a lot of uranium deposit, UF6, I believe, uranium hexafluoride. That we mine, and that it's pretty well available here in the U.S. So power and energy are those things that we need to pay very careful attention, even as we go through the transition, not forgetting that firmness or the energy content is very much needed as we go forward. Okay. And so here's another example of firmness, and I'm not going to spend too much time on this figure, but each time we look at the peak megawatts on peak hours from 2016 to 2025, the whole idea of this is when we had these peak demands, who are the players that we kind of depended on. And so if you look at each of these events, around 2016, December 19th, through the winter storm Elliott that was December 23rd in 2022, the big players are these bars here in black and in light brown, I guess. And the ones in green are nuclear uh, and blue, light blue is hydro. And you can see that when you needed to meet peak demand, hour. By the way, the peak demand is a unit of measure is always hours, so it's kilowatt hours or megawatt hours. So you look for that kind of capability to be able to dispatch. And when you had to look at these events, that you needed to produce electricity. In other words, if you're not able to meet demand, people will be out of power, and that could be a dangerous thing, especially when the weather temperatures are not very friendly. So again, in the U.S., yeah, I guess this is from 2016 to 2025, we've always been relying on fossil fuels to be able to save our butt, as it were. Uh, and never mind that even in this period, uh, 2016 to 2025, there was an enormous expansion of renewables. They were generating energy. But the energy at the crucial times was we were always dependent upon our fossil assets, and makes it more clearer than what happened in Germany. They were obviously um, very progressive in how they wanted to look at climate change. They did the same thing that Western Europe and the USA did, was kind of promoted renewables in a big way. And it was, in fact, in some ways, it was shown to be the most cost effective. The levelized cost of electricity was consistently less than coal plants and other fossil plants. Again, a megawatt is not the same as a megawatt is not the same megawatt. Even though it comes from the levelized cost of energy, LCOE being one of the least, you can see that it played a much more important role, I mean, the fossil fuels, in making sure that you were able to get the energy when you wanted it and where it was wanted. Very important. So, and I'll kind of go through this. I really want to thank one of our colleagues who's also on the Industry Advisory Council, and that's Mike Caravaggio, who's with EFRI. If you were to follow him, he's got these wonderful graphs that he was always posts, and I kind of very without any guilt, I'll be utilizing some of his data. So here's some interesting facts about Germany. In 2024, the peak demand was about 76 gigawatts. Yeah, and the wind and solar plus solar capacity was about 170 gigawatts, and the dispatchable generation was 87, and battery and pumped hydro storage was 22 gigawatts. So if you look at the electricity loading for 2024, and this graph shows this is called a heat map over 24-hour period, looking at the entire year from January 1st to December 31st. What was the highest demand of electricity in Germany? And it occurred sometime here, which is the early part of January, and then that was 76 gigawatts. And the lowest demand was 32 gigawatts in the fall period. This is when solar and wind played a big role. Now, if you were to look at what it was, what was the hourly load, less solar, all right? Less solar. In other words, what was, if I were to remove all instances where solar was used to reduce the peak load, I'm still using 74 gigawatts of load uh, without solar, and the minimum is 3 gigawatts. So you can see if I were to go back, I've dropped the peak demand by 2 gigawatts by using conventional resources. Oops, sorry. Um, Whereas I was able to reduce the uh, the lowest demand by a lot more. In fact, almost 29 gigawatts. Now, if we were to look at the hourly load, less solar plus wind, I dropped that down to 66 gigawatts. In other words, I'm using 66 gigawatts of my conventional resources, fossil resources, to meet peak demand. And guess what? For the lowest demand, the least demand, I'm very comfortable in utilizing solar and wind. So much so that I'm using 7 gigawatts less of conventional generation. So this is it's very dramatic. So if you were to look at again the same graph I showed you before, these are the assets in Germany. The solar capacity reduced Germany's peak by 2 gigawatts, or essentially by 0.02 gigawatts for every 1 gigawatt of installed solar. Let's digest that. So the useful work I'm getting out of my solar assets is 20 megawatts for every gigawatt installed solar. You know, it shows how difficult it is to meet peak demands. So by building solar, by building wind, you know, I'm doing a good job because it is kind of producing electricity and producing clean electricity at all at many times, but not all the time, and not at the peak time. And so this is a kind of very important lesson at the expense of Germany, unfortunately. But they reversed. They were relying on very expensive resources from Poland, you know, from the neighboring countries, from their fossil plants, because you know, Germany have basically shut down all their their fossil plants and their nuclear plants, and it's so
Hi, hang on a
ironic.
sec. Turn this off.
I'm sorry. So, there's a question. Okay. Um, so anyway, what it shows, it kind of is a long way of saying that this has been a very important lessons learned for the world. You know, this is over a decade of using this is where they realize that this is we need to pay equal attention to the firmness, the dispatchability, and this is what I've been saying all along. We saw these two things to be simultaneously true. We generally got more, like we had planned, more total annual megawatt hours. You know, in other words, we were kind of decommissioning a lot of coal plants and so on, but also making it up with solar. But at the same time, at the very same time, we only marginally reduced the need for other capacity, and that need is to meet peak demand. Somewhat sobering, but nevertheless, kind of a very important lesson as we go forward. Um, and I'll just concentrate on this graph here. Uh, you could see that in 2000, again, Germany again, Germany had a very small amount of wind and solar. Capacity was maybe, I would say like 40 gigawatts or so. And the capacity, you can see the fossil plants were reduced from 80 gigawatt to 76. Uh, Not much, whereas the total capacity uh, of renewables was tremendously, uh, what, almost 10 times higher. Um, so again, so we've seen the importance of renewables. They were able to supply um, green energy when needed. I'm sorry, uh, when it was needed, but not exactly when it was crucially needed. And nuclear energy, I think, plays a strong role. This again, I had a podcast 3 or 4 years ago, which again kind of goes over some of the same things, but perhaps not with the kind of emphasis that is there today. So that was like 4 years ago. Again, the same story. Nuclear capacity is a small part of the total capacity here in the U.S., but the amount of energy it contributes in 2019 is, you can see, is almost double. Um, and why? It's because it's a firm source. It can be dispatched. And especially if we keep the maintenance, if we keep maintaining nuclear plants in the way we've been doing for the last 20, 30 years, we could still operate the nuclear plants that have been built. Uh, no actually, only one nuclear power plant has been built since the 1970s. Uh, the U.S. has roughly 100 nuclear plants, by far the highest total amount of energy that's generated in the world. Although France is a close second, I'm sorry, it's a distant second. It generates 80% of its capacity, 80% of its capacity through nuclear. So France has taken a tact, and they've had this nuclear plant since 1970s, 1980s. So they've kind of been almost fully nuclear. Their portfolio is 80% nuclear, and that has its drawbacks too, because when there is a risk element is high for nuclear energy, you could see that France could be somewhat exposed to those risks. Life cycle carbon emissions from nuclear is also very low, in fact, lower than wind and solar. A pleasant surprise. But you can see that the emissions from coal, as 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 projected, is going to be the highest. Gas and some biomass are also in that figure. But you can't ignore the life cycle carbon emissions from the traditional uh, uh, renewable resources. But nuclear cannot stand all by itself. It can produce energy on a scale, and also it's clean. So what's there not to like, as I say? Um, I'm going to skip over this. I just want to point out to a work that was done in the Capstone project by one of the students here. This was done in actually during the time of COVID, and I'll kind of quickly go through what this graph is saying. What I've plotted is discount rate is the rate that you'll be charged for borrowing money to build plants, and the subsidy for parity. In other words, when should when is nuclear desirable to the alternative then and even perhaps now, where combined cycle gas turbines (CCGT) were the norm? What the carbon pricing should be. So, for example, if the carbon pricing were $10 a ton, let me get my $10 a ton. And these are the three scenarios for high, medium, and low gas supply. And I think I have this right. high, medium, and low. Anyway, the the curve here is where there's parity between NuScale, which is a small modular reactor manufacturer, that with public funding, if carbon were $10 a ton, it is competitive with with what am I trying to say? If nuclear, if the pricing were $10 a ton, uh, with public funding, it could be it could be attractive at a 6% discount rate, as it were. If the price of carbon were higher, it makes it uh, more expensive at 9%. So this was if this were $10 a ton, and by the way, $10 a ton was something back where the Congress was very close to voting on, and there was one dissenting vote. This could have been a law, but that's not a bad figure to look at. I think today probably maybe the accepted value may be less than that, but anyway, so there was a interesting. Project that was executed by one of our capstone students. Um, I think I was, oops, sorry. Five important tasks looking forward: AI-driven data center demand. As some of the demands that are being made, or at least projected, for data centers. Let me move this guy out of here. Um, everybody agrees that demand is going to go up, but nobody knows by how much. There are all sorts of projections, but really, this is really significant because over the last 30, 40 years, electricity demand has been very flat. In fact, this is as flat as it can be. There was an increase between 1990s and 2007, but it's flattened off. But now it's supposed to be it's going to shoot up again. Um, and so this introduces all sorts of problems. Least of it is the technology behind it. Most of it has to do with what are the roles of the different uh, stakeholders. Uh, they're projecting that AI-driven data centers could demand as much as a nuclear plant. And you probably follow the activities. You have the Microsofts and the Amazons and others who are kind of buying up, or at least wanting to buy up, corral dedicated power plants. Some of them are looking at nuclear because, as I said before, nuclear is inherently green and it's highly dispatchable. And they're looking at all that energy coming towards their asset, uh, data centers. But this probably will cause a lot of commotion. You and I, as part of the population, may have to feel a certain kind of pain that was not before. Remember, electricity, because of scale, because of transmission lines where they could have the generator far away from the population center or the load center, that we could have such low prices for electricity. So this first bullet uh, may indicate that that may not be the case, or something more dramatic. The business model itself may be very different. The business model, for those of you who may not be very familiar, is that all utilities get a monopoly to operate in a certain area because they are kind of their rules. They're governed by a PUC, a Public Utility Commission. And you can well imagine that the Public Utility Commission, utilities innovation should take a stronger role. But if you wanted reliability, if you wanted the cheapest price, you had to be, pretty meat and potatoes kind of guy because you can't afford to have a innovation that does not work out in the marketplace and have the ratepayers foot the bill, as it were. Um, Increased nuclear, again, that mantra is, I still believe, that is one of our very strong suits. We should strongly proceed in the direction. Here's another area for batteries for long duration storage. There's been a lot of advances made in this area. In fact, I'll show you that one of our speakers in our seminar is for a future seminar this semester is with a company called Form Energy, which is going to be looking at this as very strong players in batteries for long duration storage. Um, so these are the five important tasks. They may be one of the most difficult, but anyway, this is kind of getting us, or probably get us to where we want to be. Maybe it won't look like what we thought it was going to be, but definitely, I think we are along the right path here. Um, so let me wrap up my presentation uh, by this is the first presentation for this uh, fall semester. We're going to hear from Dr. Frank Felder on resource adequacy and modeling. Again, this is one of those inside baseball things for the utilities. The more the demand, the more the resource adequacy mandates, almost three times. In fact, if there's more need for more demand, this is going to be even three or four times more as far as what the resource adequacy would be required. On the next one after that would be from EPRI, looking at bats and wind turbines. He is listed in his resume as a expert on bats, a biological expert. So it'd be interesting to hear this talk. The remaining talks are all by past graduates of this program. From Jasper Chumba, we'll talk about managing the grid edge and looking at behind the meter assets, unlocking the value of multi-day storage by Vince Aguilar, who was a graduate from 2021, I believe. We have a number of our graduates with this company, Dernet Soft, who are playing a very strong role in virtual power plants. Again, you will hear more about virtual power plants. And we have three of our past students. Net zero multifamily homes was a capstone project that was pursued by Alex 2 years ago, and he's in a business where he's involved in that. And finally, Laura Marsiglio, a 2021 graduate. She's a senior analyst with National Grid, and they'll talk about their 70-30 plan in New York, as well as the low carbon initiative. Here are the capstone projects that we'll be looking at. These are still being kind of expanded. We have a larger cohort of students, somewhat unexpected, but I'm not complaining. I think it'll be really good. It's really good that we have a much larger contingent of cohorts, and hopefully we'll have a lot more things to report on this capstone project as we go forward. Now, I think I overshot the runway by quite a bit, and let me just share this because, again, graphics show a lot of things. This shows what is the electrostate countries that have made advances along the x-axis, which is along the y-axis. Let me put it. This is the amount of change in wind and solar generation as a share since 2010. And this is, what does this say? What can it say? Take this out of the way. No, this, okay, the electrification increase since 2010. This is the percentage of increase in electrification. Remember, I mentioned electrification is the route for meeting the climate goals. So the more you have electrified, and the more resources you have for wind and solar since 2010, again, the benchmark being 2010, you fall somewhere in this graph in this region. So the higher you are in the right corner, right top corner, the more, let me say, you're more aligned with some of the capabilities that are asked for. And look at China. I mean, this is something that they've taken a very strong leadership role. They are head and shoulders beyond any country. Vietnam is kind of interesting the way they kind of they are a country that was beaten 30, 40 years ago, and there they are. Point out that India again is trying to mimic China. They have some ways to go. There are others. Mexico, our neighbor, is pretty well advanced, and here we are. The U.S. is unfortunately has not gone too far on the x-axis, but I'm hoping that we will be there in hopefully less than a decade, out somewhere here. Kind of interesting way to depict this, but you can see that a lot of countries are pretty in the left bottom, with very few in the top right. Okay, I'm going to stop here, and I know I've gone through a lot. I hope I didn't put you to sleep, but it's really exciting times for new students to come in and look at these problems, because it's problem solving. In fact, our mission statement and our program is problem solving. It's not something that can be done overnight, or it's not some genius who's going to come up with a solution. That can and may also happen, but it does take teamwork. It takes a lot of people to be able to reach some of the goals that we need to reach. Okay, I'm going to stop talking. I'll take questions. So, let me stop sharing, and I'm going to stop sharing. Okay.
You have to hit the share, that little green button, and then you can click stop sharing.
Oh, okay.
There you go.
Okay. Let me get the, how do I get this one? Okay, here we go. All right. So if you have any questions, please raise your hand, unmute yourself. And go ahead. Any questions?
We have a question.
Professor,
Can you hear us?
can
Yes.
you hear us?
Yep,
Professor?
go ahead.
Are we meeting later on as well then to discuss?
Oh, wait, no, okay, we can talk about, this is questions for about the
Oh.
talk that Professor
Talk.
Shankar just had, which we give preference to the students first. So just introduce yourself and then ask your questions.
Anyone?
Okay, Amin, you have a question? Amin, go
Yes.
ahead.
Yes, thanks for the presentation. It was really nice. I have maybe two-part question. One of them is that when you were trying to explain the capacity, essentially capacity factor of each one of like the available resources, one element in it, I think, I don't know whether it's been considered in your calculations or not, and that is the grid, the existing grid that we have, which is like centralized, and it's just like have a specific characteristics based on the major population regions. And as you get away from major population regions, you go to the edge of a grid or you go off grid, I think that calculation is going to be completely like different. What I mean is that that's like, I think the per capita calculation for that energy consumption would be interesting to see as well. And the other part is that, how do you see the future of a smaller scale, decentralized utility energy generation for this future that you mapped?
Good questions. Good questions. I mean, first of all, a national grid, when done right, is the right way to go. I don't know if I made sense there. If you look back in the 1920s, 1930s, 1940s, when the grid was developed, they had this framework as to how this grid will work, function, and they built all the interconnections as they planned. Um, China has taken that route. I mean, they have so much renewables. I mean, as far as the numbers are concerned, because they would able to do this quote central planning. I'm not an advocate of central planning, but that kind of takes care of areas that we are running into problems. Interconnection, the permits are take so long, and not only that. But the cost is humongous. There's nobody bellying up to the bar to take that risk, as it were. And we are a 24/7 economy. We can't afford to have any brownouts or blackouts. Blackouts are the worst. So really, there needs to be some central authority which needs to be talking about these big issues, the firmness issues. I strongly believe that the other parts of the market, the vendors for renewables, they should be market driven. The other thing that the events in Europe showed, in Portugal and Spain, that some of the restrictions that they placed on renewable vendors sometimes has a negative effect. So, what can happen with if we don't have the proper guardrails, you could have some serious issues. So, the idea of having several microgrids, kind of autonomous, is a possibility. But really, we're missing out. If we do that, we are missing out on something that grid offers is basically insurance with a lot more people involved, and the pricing is also important. Once upon a time, this electricity was considered pretty inexpensive. It's something that you looked at an electric bill. I'm sorry, you rarely looked at an electric bill because it was a very small portion of your disposable income. And now we take very strong looks. So it's possible, but really the idea of scale is really, if done right, it could be to the benefit. I don't know if I answered your question. I mean,
Oh, yes, thank you.
Abigail, you had your hand up. What's your question? Please unmute yourself, introduce
Hi.
yourself.
Hello, I'm Abigail. Can you hear me?
Yes, I can
Yeah,
hear you clearly. Yeah.
perfect. So I was wondering, for increasing reliance on nuclear power for the US and honestly even for France now, having so much of your capacity be nuclear, is that an issue for sudden like natural disaster type things like a huge heat wave or a cold snap where you need a bunch of heating or cooling because like nuclear takes a long time to ramp up and to slow back down, right?
Yes, you know, you're absolutely right. I mean, um, I think having you actually minimize risk by having a variety. Um, you know, say we have you know, looking at a future world where we get deep geothermal power, that could be the kind of the panacea. And at the same time, kind of nuclear fusion. I mean, life does not get any better. But if you were to concentrate on one of them, it's a single point of failure, which is always the danger. You're exposing yourself to risks that you could minimize those risks by having, you know, geothermal and nuclear fusion, if you're so lucky. Deep, deep geothermal, you know, we think is kind of the answer to a lot of things, but who knows? You know, there could be some issues. If I'm going to go like, I don't know what they talk about, several hundred miles below the Earth's surface. I don't know. We've never done that before, and I don't know what kind of risk that we undertake. But if you were to kind of have two, three strong resources of, you know, you feel a little bit better. And that's why you know you invest your money in bonds and stocks so that you kind of balance out the risks, as it were. So, um, Abigail, I don't know if I answered your question, but I kind of gave you kind of a general answer on that.
Yeah, that was perfect. Thank you. I was mostly concerned that like the green options that I was thinking of, wind and solar being intermittent, aren't like necessarily reliable for an emergency. So you'd kind of have to fall back on coal or natural gas. But
Yeah.
I'd forgotten about geothermal. So thank
Yeah,
you.
yeah, and don't forget, intermittency is really where the firmness issue was kind of brought up, and it kind of challenged. You know, why our focus on clean energy? Why not the focus on firmness? It kind of woke us up. It woke me up because there is an answer. If we had storage, large duration storage. What I mean is, you know, the days of plentiful. Remember, I don't know if you remember the German graph I showed with all the solar and wind. They were able to reduce the conventional uh, uh, resources by 7 gigawatts. That's very helpful. Now, if 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 that can be achieved, uh, you know that can play a very strong role. Any other
Awesome.
questions?
Thank you so much.
Thank you, Abigail. Uh, Anybody else? We have a few more minutes. Oh yeah, we have about 5-10 minutes.
Rudy, I think there was one in the chat from
Oh.
earlier. I hope I'm pronouncing the name right. Kamal asked about slide number 8 of yours. Says where you present generation capacity and electricity generation, which year these
Yeah, I
are
think it was
data
20.
for.
Kemal, thank you. That was a good question. It reminded me this. A future slide told me I think it's 2019. All right. I'm looking at the chat box. Okay. Jump to the latest. Okay. Here's a question. Eric Forson. I'm a petroleum engineering graduate interested in. Okay.
He's asking about the
Okay.
program.
All right. All right.
I'm sending a
Sorry about
separate message.
that. Okay. Any questions on the talk today? Okay. Hearing none. Any from the students who are in the energy lab? Obviously. Okay. All right. So I think why did we call it? Again, going once, going twice. Yeah. All right, Susan. I guess we are done. Thank you all. Thank you for your patience. After the Labor Day break is by Dr. Felder. He's an authority on adequacy of resources. You can see what the challenges it could be when we're having demand increasing. That could be a big issue. And on to towards the end, we're looking at what some of the activities are in different utilities, uh, and really one of the bright spots is renewables with storage capabilities are kind of starting to play a big role in California. They are kind of reducing the use of conventional resources, carbon-based resources. So that's good news. So I hope that continues as we go forward. Thank you all for your attention, and look forward to seeing you a couple of weeks from now.
Thank you, everyone.